constructed, a set which was the intersection of all inductive sets. And we called that, so that is a unique object. And we called that, so we have a set. But there are a lot of properties this set must satisfy. It has to satisfy addition property, multiplication property of integers. It has to satisfy PMI.
What is PMI?
What is PMI? Someone answer that.
Principle of mathematical induction?
That's right. Principle of mathematical induction is such a long phrase. We might as well shorten it. Sai? Sai, do you have a question?
Yes, sir. So you told the addition principle of integers. What are integers?
What are integers? We are going to be talking about it shortly.
Okay,
so, in the notes I sent you, we will have the description how those are done in this set. After all, it is a set. How can you have addition and multiplication in a set? Right? You understand? So, for example, here you are in a set of people. How can you have addition and multiplication of people? And that is where this successor of a set comes in addition, and multiplication is actually addition. So the main thing is, what is sigma n? Oh, sometimes I call it sigma n. It's Sn. Sorry. It is Sn. So it is defined in terms of addition. Once addition is taken care of, multiplication is taken care of, because multiplication is repeated addition, right? And we also have a cancellation law, things like, I'll be with you. If n times L is m times L, that should imply n equals m. Things like this. All these rules that we usually have for integers should fall out of our description of it. So that's a slightly long topic, and I will send you the notes for it. Yes, questions?
I think I have a definition for addition.
Yes.
So this is the definition. A plus B. Instead of M and N, I'll use A and B. That's a bit easier. A plus B is equal to. So basically, you start at A, and then you keep doing S of A, S of A, S of that, B times.
Yes. True.
So it's like similar. It's quite similar to multiplication. For simple, I'll just write SB of A. SB of A is A plus B.
Right. And that is the idea there. First of all, they will start with n plus 1, we know is S of n, isn't it? That is our basic assumption. And from that, they continue with this. So let's assume for now that addition, multiplication, and all other properties are defined. So we have this set now looking exactly like the natural numbers, let us say. How do you then get the integers? What are the integers? Integers are, Siddharth,
These are the integers. So we've considered 0 as a natural number, right?
yeah, we should.
Then the integers are the natural numbers plus the negative, minus 1, minus 2, minus 3, on and on and on. Actually, it's natural numbers, negatives, and the big 0 right there. Love that fan.
Yeah,
0
well,
is the center of everything.
Our problem is we don't have the concept operation of negative defined on our set n. We don't know how to define negative. So what to do? This is where not only that, if you said that 2 minus 1 is a certain integer, well, it could be 3 minus 2 also, isn't it? So we have some issues. And in fact, there is an infinite number of ways of defining it. This is where an equivalence relation. Do you know what an equivalence relation is? What is a relation? Suppose, what is a relation on the set A? It is any subset of. Good. Who wrote that?
I wrote it. R is a subset of A cross A, and then equivalence relation is a special relation which is reflexive, symmetric, and transitive.
Exactly. So let us take a subset of n cross n, because our A is n. A subset of it. So it's a relation, and as Siddharth said, it is reflexive. Not this. This here is reflexive. Symmetric and transitive. So let us take a relation that is an equivalence relation. So I will in fact denote it by E. So define on n cross n, Siddharth.
Use that partition trick you taught us.
Yeah, we could. But
for example, that's an equivalence relation.
Yeah, yes. We have another one here. So it is a subset of this. So the elements, if it is a subset, the elements of this look like n and m, ordered pairs, don't they? The elements of this look like ordered pairs. So how are the ordered pairs related under this E? So this is how they are related. N, M is E related to N prime, M prime, if and only if N plus M prime is N prime plus m. What? First of all, is this reflexive? Is this relation reflexive? Let's check it. Is nm related to nm? N comma m is E related to n comma m. So I have 3 people already agreeing to that. 4 and possibly more. Let me transfer you guys to a place where I can, yeah, hey, I have an idea here. If I expand this way, I might be able to see everybody. Let's try that. Where is my, no, I'm having trouble. All right. It is reflexive. Is it symmetric? And is it transitive? That's a little bit harder to check, but you will see that it is. So here we have a reflexive, here we have, yes.
Actually, I have a slight doubt. You won't write like 2 ordered pairs are E-related. You'll write 2 numbers are E-related. NEM.
There is a reason for this way, funny way of defining it. Okay. The reason is we want to have n minus m. If n minus m is n prime minus m prime, we want nm to represent nm and nm and n prime m prime to represent the same integer. Well, let's see what that means. Because if this is true, isn't this the condition represented here? This is what is represented here. N minus m is n prime minus m prime. And if we can relate this, if we can identify this with this, because this along with this satisfies this, follow? That is, if we can do that, then we can avoid difficulty arising from this. So here this will be your n, this will be your m, this will be your n prime minus m prime. So nm is related to, related to 3, 2. Follow? Two, 1 and 3, 2, as far as this equivalence relation is concerned, are the same. So that way I can represent 1. On the other hand, now I can represent minus 1. How? minus 1, 0 minus 1, all kinds of them. And that is what? 0, you see, 0, 1, 1, 2, 2, 3. Oh, I made a mistake. E related. Are you with me? This means that all of these are in the same equivalence class. So if you take any one of them, that set is really the set of all these. So you see, that way we can identify all of these things into any one of them. So that is what I call now an integer. Clear? So using the natural numbers, I have produced the integers without having to introduce a new symbol minus 1. So we can represent minus 1 like this. We can represent, how do you represent 1? Swasti, give me the equivalence class corresponding to 1.
Sir, I actually have a question. I didn't get it. Repeat.
Yeah. Go ahead. Oh, you didn't get it? Okay,
Yeah.
Sure. You see, on n cross n, there are lots of things. 1, 2, 2, 1. On that set, every set can accept equivalence relations. Okay, so we can put an equivalence relation. This equivalence relation is on n, by the way. Okay, so equivalence relation is a subset of this that satisfies these properties. So on that, what is this equivalence relation? It is defined like this. Why did we define it this way? Because we want nm and n prime m prime to represent the same integer. Because 2 minus 1 is 3 minus 2, and so on, and that is still 1. So if I have 2, 1, 3, 2, 4, 3, all of them in one equivalence class, this ambiguity is taken care of. All of those represent just one integer. That is what this equivalence relation helps us do. It squeezes an infinite number of these pairs into one set, which can be represented by any one of them. Follow? And that one is called an integer. In this case, what is that integer? 0 minus 1. We don't call it minus 1 because there is no minus in our theory. We have a plus in a sense, but we don't have a minus. And this will allow us to introduce the minus sign. 0, 1, therefore, is related to 1, 2, so that we can do this, and what comes out in ordinary arithmetic is minus 1. Follow?
Yes.
So
Okay.
this is a way of representing the negative numbers as well as the positive numbers as a pair of numbers. After all, what is minus 1? It is 5 minus 6. The problem is, it is also 7 minus 8. So all of that, so 5, 6, and 7, 8, and all the others are in one class, namely the 0, 1 class. Let's get used to that more. Let me I think integer construction. Let me check something. Can you Google integer construction? Let me see. Integer construction. There is a picture I am looking for, which that may be difficult right now to get. And so I will go back. Siddharth? Yes, Siddharth.
Actually, I saw a picture containing ordered pairs 0
Ordered
0
pairs.
0 1 1 0 2 1. I saw, and
Yeah,
those
do you know how to share that with us?
Sir, can I do that? Sundar
Yes. Oh, that will
I
be
think
good.
it is in
Sundar
Wikipedia.
Raman, can you do that?
You'll have to stop sharing, sir, for a second.
I should stop sharing.
Yes, sir.
Okay, sir.
Uh, okay, Siddharth shared it.
This is the one.
Yes.
And enlarge it. This is the one. Enlarge it. Good. Can everybody see that picture?
Yes, sir.
So you see, this whole thing is an equivalence class. Is it? All of this represent the integer 0. This is the equivalence class of 0. This is the equivalence class of 1, 2, minus 1. So you see, there is the set of integers. It is a representation. Thank you, Sundar Raman. So, do you now get a little feel of what this equivalence relation does? This equivalence relation arranges the members of n cross n into groups representing the various integers. Agreed? You saw those groups. The point is, what do you do with that? Okay, so you have a set. You have a set, n cross n, and you are getting out of that the equivalence classes, but this and this is, what is this here? This is really all those lines that you found, isn't it? Those lines, those were the integers, because they were representing all of those. They were the representatives of those members of the equivalence class. So after you get this, what you do is you take just that. And what is that? Those are the standard integers. But do you have, we have minus 1. So now, after you get this, how do you add and subtract? How do you add and subtract? First of all, before we do anything, we need to have, how do you compare two integers? Well, here is, we are going to define less than or equal to on, we are going to call this set, we are going to call this set we are going to, pretty well, we are going to call this set Z. Define Z, define this on Z by, well, NM, forgot. Take N, take M. This is in some equivalence class. Now that class is less than or equal to this class if and only if N plus M prime is less than or equal to N prime plus M. That is, let's get familiar with that one. Well, let's see. Let us find the equivalence class of, is minus 3 less than or equal to minus 2? In standard way, minus 3 is less than or equal to minus 2. Agreed? Minus 3 is less than or equal to minus 2. Now, can you give me a representative from the equivalence class representing minus 3? Remember, these are the numbers: 0, 1, 2, minus 1, minus 2, minus 3. Can you give me a member of that equivalence class of minus 3? How does minus 3? Yes. There's 2 people, 4 people. Okay. Sai, give me.
Sir, 1, 4.
Say that again.
Sir, 1, 4.
1, 4 is a representative. Therefore, this class will be the set of numbers like this. Agreed? Any one of them from there. Give me something from this class. Amol, where are you? I can't see your face.
So 3,5, 2e5.
Amol,
Yes, can you hear me?
I can hear you, but I can't see you.
Oh, sorry. Yes.
Okay. Can you give me a member of the equivalence class that represents minus 2?
3,5.
3, 5.
Yes.
According to our definition, this will be less than or equal to this if and only if what? N, M, N prime, M prime. N plus M prime, 1 plus 3 is less than or equal to 1 plus 5, sorry, is less than or equal to 3, M plus M prime. No, N prime plus m. You see? So this works. Oh, just because I showed that one of them works, I cannot pronounce that it works. This could be a homework that this situation will take care of all the n less than or equal to m. That takes care of what do you call that? The binary operation of comparing in the integers. Yes, question.
Yes, sir. Sir, so over here you've defined less than or equal to, but then, sir, you've again used less than or equal to in your definition.
Ah, that is a good one. That is a good one. This is known to us. This is not known to us. We are trying to interpret this using this one.
Got it, sir.
These two are really different. This is different from this one.
Yes.
We could say that, the confusion. That's a very good question. I should put this symbol for it. But I didn't because I didn't. But this is what is meant. Follow?
Yes, sir. Thank you,
This
sir.
will be like this. That's a very good question. Okay. Now let us see. So we can. Wow. So we have obtained the negative integers. So now all that is left is addition. Let's now start the algebraic operations. Algebraic operations with integers will be. So take an integer, which in our case is now like nm. Take another integer, which is like n prime, m prime, and their addition is n plus n prime, m plus m prime. Will that work? Let us take 2 plus 3 equals 5. See if we can get it. Give me the equivalence class representing 2. 2 will be, yes.
Sir, 2 will be 3. 5 and 3, sir.
Anything from that line, remember?
Yes, sir. So
Anything
5 and
from
3.
that line. 2 was here, 2 0 was here, 3 1 was here, 4 2 was here. I think we'll take let's say 2 0. That's the easiest. So 2 0 plus, and what is 3? 3 will be 3 0, wouldn't it, Jayaditya? So now it's going to become easy. And is that what? N plus n prime will be 5. 5. M plus m prime is, there it is. Equivalence classes, this addition behaves like the normal addition. Follow? And that's the big operation. As soon as you have addition, you have a lot of other things. Let us see if it can even represent subtraction. what is n m minus n prime m prime, and it is defined as, this is code, n m plus m prime n prime. Let us see if that works. Let us take 2 minus 3 equals minus 1. Is this going to give us that? What is 2? 2, 0 minus 3, 0 equals nm is 2, 0 plus what? Something wrong.
No, sir, it works.
Something wrong. Yes, Sai.
Sir, did you mean the opposite? So it means 0, 2?
This might be
0, 3. 0, 3 instead here. So maybe
this,
that will work.
this might be this, yeah. How do I get 0, 3 there?
Because m prime, sir, m prime is 0.
Yeah, m prime, n prime.
M prime is 0, n prime is, you can see 3.
Oh, I see. 0,
So
3.
0, 3, you mismatched.
Good. I didn't know that there is a flipping there. Follow? So good. So that, and that one is, according to this, it will be 2, 3, which is representing 2, 3 represents minus 1, doesn't it? Strange. Some people have spent years thinking about it and come up with these ideas. Okay. Addition, multiplication. Only no. Addition, subtraction. Let us multiply 2 integers. And that is defined as n prime plus m prime n prime plus m prime. Oh, let's see. 2 times 3 equals 6. So we will have 2. Give me a pair representing 2. What is 2? The simplest one is 2, 0, isn't it? Is 2, 2, 0? And this will be 3, 0. Well, we could take 4, 1 and so on, but this is the simplest one. What is that according to this? This is n prime, m prime. It will become n prime 6 plus m prime 0. This bracket is different from this bracket, okay? n prime is 2 times 0 plus n prime, which is 0. So I am confused with this brackets. I'll put a bracket. Let me move this here. No. And then I will put my bracket. Did I make a mistake? And that is,
Sir, I
that
think
is
I think
6,
it should be
0, which is your 6. 2 times 3 is 6. Yes. Sai?
Sir, but won't this be the same? So when you're doing for an equivalence relation, like for 5 into 10, let's say, all you need to do is 5, 0, 10, 0, and then the second term, no matter what you do, it becomes 0. So we just need to do 5 times 10, and then
That's
we simply
right.
get the answer.
So from now on, exactly. From now on, we don't have to go through this. We were only verifying if this works. Follow? From now on, we know that this is 6, 0. Simply multiply. You don't have to go through this. You can. Actually, what you need to do is, we have to verify this in general using algebra, okay? Rather than check in every case. So, so one homework could be, which I am not giving, verify that these operations what do you mean? These kinds of things are in fact are the operations, standard operations on Z. So we have constructed N, we have constructed the integers. Now we can go ahead and construct Q. I know that we are going a bit too fast now, but it doesn't matter because you have the foundation. So because you have all the integers, you can now represent Q as ordered pairs A, B. So how do you represent that? So you again do the same thing. This time you look at a relation, equivalence relation on Z cross Z. Okay? And that equivalence relation is, let's call it E prime or something. A comma B, now these are from Z, E prime related to A prime, B prime, if and only if first it will look like very long, but you will get used to this. A B prime equals A prime B and B equals not equal to 0 and B prime is not equal to 0. We will do examples. Or B prime and B are 0. let us see. Then Q is, I'll come back to this, okay? Q is, what do you think Q is? Q is the set of equivalence classes AB of AB, where A and B come from Z and B not equal to 0. There is your rational numbers. Where AB is an equivalence class of E prime this time. So, how does this look like? Sundar Raman, can you work on getting another picture?
Yes, sir.
It will be neater than the one I can produce.
Sir, what to, sir?
Take your time, but hurry up.
Yes, sir. Just a second.
If you find another picture, I will stop sharing. Swasti?
Sir,
We
we
haven't
cannot
even-
see,
Yes,
cannot
yes.
see the video.
Yes, sir.
Say that again.
We cannot see your video.
Say again.
We cannot see your video.
Oh, that's because I stopped sharing probably.
No, sir, there is something on your video, a paper or something.
Oh, you are right. I put it. Oh my goodness. Now you can
Sir,
see.
Sir,
Thank
I'll
you.
share my screen.
You share your screen, so I am going to. Yes, sir.
Yes. Just a second. Yeah. Sir, can you see this?
Well, let's ask everybody.
Can you see this screen?
Yes, sir. Yeah, let's get that thing
Yes.
to fill the screen.
Uh,
You will come eventually. You got it last time. We will play with you.
yes. 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 Yes, sir.
Raise it. Good. And here is the situation. Just like integers could be represented by several pairs, rational numbers can be represented by an infinite number of fractions. And all of these are represented by this, any one of them. So we take the simplest one. Can you hear me?
Yes, sir. We can hear you. Yes.
So any one of them is a member of that equivalence class. So let us take all the ones on this line. Here is a member of this equivalence class. Here is a member. So you see, these are the rational numbers. But how do you get, wait a minute. Wait a minute. No, there is a problem. 2/3 is 2/3 is not equal to. Wait.
Sir, I think this is the wrong picture. I think this is
This is the wrong. Let's get
Yes,
another
yes.
one.
Yes.
These are. This picture. Before you leave it, these give all the rational numbers. You follow? Okay, let's hold on. These are all the reduced rational numbers. Follow? So they are saying you can count the rational numbers by arranging them like this. And this is a proof of the countability. Now let us go to another picture for the one that I wanted. Try another one.
Yes, sir. Yes, sir.
These are all about countability, isn't it?
Yes, sir. Yes, sir.
It's hard to find one rational numbers as equivalence classes. Yeah, good. See if we can keep going for images.
Yes, sir.
Maybe this one will work. This one. So 1, 2, keep going, go up. This one. The third one on the left from the top. Third one on the picture. Third one on the left from, this is 1, 2, there's one below here. Third one
Oh,
right there.
yes, sir. Yes, sir.
This one. Get that picture.
Just a minute, sir. It's loading.
That site can be reached because so when you try to visit it, it's not giving it, is it?
Yes, sir.
Yeah, that's kind of smart for them. They probably want us to subscribe or something. So we will get what they got instead of visiting.
Yes.
So
Yeah.
go back there again.
Yes.
Okay, let's say that. Let's just see what it is. Can we make this bigger by not visiting? So anyway, look, they have here 2/3. 2/3. Can you see 2/3 in this picture? Yes. And there are other members of that equivalence class. 2/3 will be the same as 4/6 should be someplace. And these are the reduced forms. Then all the infinite number of unreduced forms are unreduced ones are here. So now we will go back to my screen. Okay?
Okay.
I think you got the idea. So let us go back to our thing.
Actually, I found the exact same picture, but a much larger one.
Okay. Can you share it?
Okay. Could you please
Sundar
start?
Raman, help him share it. He's a good
Yes,
guy.
sir. Yes, sir. If you stop sharing, he'll share it.
Yes, sir, I did.
Yeah.
Oh, excellent. So half is related to 2/4, is related to 1/2, and so on, and it keeps going. The infinite number of members in the equivalence class of 2/3. is represented by 2/3 or any one of the others, but the reduced fraction is a simpler looking representative of this class. Beautiful. So there are the rational numbers. Okay, now we can go back to our old screen. All I have to do is, thank you, Siddharth, thank you, Sundararaman. It is wonderful that we can bring these pictures. You know, about 50 years from now, you don't even have to go to a lecture. You can just directly download it into your brain in 1 second. So right now we are not there yet, but I feel sorry for those future people. They don't have the experience. In fact, you don't have to go to school at that time. You can just plug your brain in there, and in 1 second you can get all of calculus instead of going to school. This is going to be all wow. Anyway, let us see here. What time is it? 8:30. So here we have 2/3 is E prime related to 4/6. If and only if, well, B is not 0, B prime is not 0. So let us see. Let us check it. We have A, B, A prime, B prime. So is AB prime, A prime, B 2 times 6 is equal to 3 times 12. So you see this equivalence relation is really doing this. A B prime is A prime B. Get it? This equivalence relation is just coding this property of equality of rational numbers. This is A B prime is A prime B right there. And we don't want in rational numbers, we cannot have the denominator 0. So two rational numbers are related in this manner. So we can quit now. That
Sir, it will be 3 times 4.
3 times 4. Okay. And we have 3 is not 0, 6 equal. Everybody agrees with that? And so if this will give us the set, how does it have the properties of rational numbers? It has the properties of rational numbers if it can add and multiply the arithmetic operations we need. So let's go and get those arithmetic operations. The arithmetic operations are represented like this. A, B is less than or equal to A prime, B prime. When is it that two rational numbers can be compared? If and only if B prime greater than 0 and A B prime less than or equal to A prime B, or B prime less than 0 and A B prime greater than or equal to A prime B. Why do they have to have this complicated? Because it will take care of all kinds of, let us say, half is half less than or equal to 2/3? Let us see if it will give it to us. 1, 2 is less than or equal to 2, 3, if and only if b prime, okay, 2 times 3 is bigger than 0. In that case, this is the one that we use. Agreed? If b prime is greater than 0, this is the one. Otherwise, we use this one. And b prime, a prime, b prime. b prime is what? What is b prime? What is b prime equal to in this case?
Sir, A, B prime would be 1 into 3, which is 3.
3. Is 3 less than or equal to a prime b?
Yes, sir.
So that is how come. Essentially what is happening is, look here. This is, can someone tell me what this is really? When is it that you have two rational numbers compared like this? When b prime less than or equal to a prime b, isn't it? Because a over b is less than or equal to a prime b prime. Multiply both sides by b prime. You get a b prime less than or equal to a prime b. That is what this is here. Follow? See, the properties of the rational numbers are coded into the description of the equivalence classes that are compared. The members of the equivalence classes should be related in this manner if you want to compare those equivalence classes. Are you with me? So this gives us the set now is really equals the rational numbers. That is how you have constructed. We have constructed the rational numbers. All right. Now we have n, we have z, we have q. We will not construct r. In the next class, I will give you a glimpse of it. And in the next class, I will, however, construct this one. That's easy if you have this one. Now, there is one difficulty with this entire operation that we were doing. Quaternions, we are not doing it. And quaternions can be constructed because they have to do with integers. Okay? This was the big one. Because we have that, we can come up with all kinds of equivalence relations, and the operations on the classes will give the operations in these sets that we are familiar with. We have one difficulty, however, and we will solve that in the next class. We were talking about ordered pairs, weren't we? We were talking about equivalence relations, but equivalence relations have to work with these ordered pairs. But there is no ordered pair notion in the axioms. Yet we were just using it. How can you do that? You are saying that everything is a set in set theory. All you have is set, you have membership, you have this subset. What is this? And you have an intersection, and you have union, and you have equality, and you have the ampersand sign. If you want to be sticky, you have the left bracket. You have the right bracket. You have the square bracket. You have the curly bracket. This is your set theory. Okay, and you don't have any comma in there really. Comma is not part of it really. There is no ordered pair. Let us say you are 8 of you. How can you say that one of you, how can I say that one of you is less than or equal to the other? How? Because one person may be bigger than another person. Let us say you are in music, but this person may be better than that person in high jump. So how do you compare two people? There is no order in a set. There is no order in a set. So how can you produce order? So we will define next class. We will define this to mean, watch this. Okay, let's have comma also. This is a set, isn't it? I say this is representing an order. In this manner, suppose you have 1, 2, 3, 4 in a set. I want 1 less than or equal to 2, less than or equal to 3, less than or equal to 4. I will put this as, suppose I make a set 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. Well, in this set, this is a set. There is actually an order in this set. Although a set doesn't have order, it is possible to produce order, and that is magic now. It is magic time. You look at an element that is common to all the sets. What is, can you give me an element that is common to all sets? What element is common to all the sets?
1.
Pick it up, comma. Cut it out. In the remaining sets, this is now the empty set, okay? In the sets that have anything in it, is there something common? 2, cut it out. Now this is the empty set. In the remaining, you have produced the order. Suppose you have 1, 2, 3, 4, the set, and you want to produce the order 2 less than or equal to 1 less than or equal to 4 less than or equal to 3. It is possible to have mathematics with this relation embedded in it. It's not the usual math that we do. Let us construct this ordering in a new set. It will be 2. What's the next one? 2, 1, 2, 1, 4, 2,
Answer 2, 1, 4, 3.
4, 3. Now the beauty is, it doesn't matter how you write this. You can write 1, 2, 3, 4. Now let us see. Is this order coming out of this set?
Yes, sir.
2. That is empty set, gone. Next one is what? 1. This is now empty set. There's nothing to pick up there. 4. Get it? It is possible, although there is no order in the set, to produce order using power set of X. In the power set of a set X, there are sets of sets. This is actually the power set of the power set. This is an element of the power set on the power set. Understand? This is the set X. These are elements of the power set of X. And this is the power set. This is an element of the power set of the power set. Now, look at this. You want an ordered pair? I'll give you one. There. Is this an ordering? Well, cut it out. X. That's the first one. What is left? Y.
1.
An ordered pair. Okay? So our definition of the ordered pair from now on will be the set A and the set AB, their set. How many of you follow this idea? So if somebody gives you, if you want a string from a set ABCD, if you want to produce a string, you can. Kondia. This is really this here. A, comma, I don't know, B, then, oh, what is that? This here. Then you have, I don't know, A, B, C, then the ADCB. Will that work? And I don't know. I'm not sure. You cut out A, so you get A. You cut out D, you get D. You cut out C, and then you get this. Yeah, it works. And so there is the order. The beauty is this construction allows you not only to get ordered pairs, you can get ordered quadruples. Follow? Thus, you can put order in a set. And we will, in the next class, show that this has all the properties of the standard order, like A, B is equal to C, D, if and only if what? A equals C and, tell me, A equals C and, yes,
Answer B equals C or
B
A
equals C.
equals.
We will
Yes,
prove
sir.
that. We'll prove the standard properties of the. It is not only enough that we represent the order in which it is represented. We also need to make sure that this object has all the properties associated with the standard way of writing it. Agreed? With that, we can close our discussion in the next class. All right.